All right. So thus far, we've covered many of the different types of stress that are applied to a body. And today we're going to learn about combined loading. What happens when we have a complex geometry and that geometry is subject to many different types of loading, right? So let's consider a 3D beam that we've subjected to many different types of force and moments. We apply a normal force F. Say we've applied a shear force V. We have two types of bending, a bending moment 1 and a bending moment 2, so two-plane bending. And we've also applied a torque to the geometry, inducing a mode of twist. This complex loading situation leads to the development of many different types of stresses within this member. And we need to learn how to deal with and combine them all together. So where do we start? Where do we begin? The first thing to do is to examine the component we have and determine our knowns and unknowns. What are the things that we're given about this geometry? Do we know its material? Do we know its length? Do we know the magnitude of those forces and moments? And then what are we being asked to find? Do we need to find the extreme value shear stress or the principal stresses at a particular location? Or do we even need to figure out through shear force and bending moment diagrams where those forces and moments are maximized along the length of the beam? Once we've identified what we need to work through, the next step is to draw a free body diagram. So simplify the geometry that we're given and apply the equations of equilibrium, sum of forces and moments, in order to solve for the reactions, the supports that support our structure. From there, we can then go and start to draw our normal shear force and bending moment diagrams for our particular geometry. If the geometry is 2D, we can simply do that one time. But if it's a 3D geometry, we may have shear forces and bending moments that develop on different planes of our geometry. If we're looking at the part from the front, rather looking at it from the top. So we could have actually sets of these diagrams that we need to find. Now from there, if critical locations are not known, then we'll need to find what are the critical distances. Where along our member are the normal forces, shear forces, and bending moments maximized? Where are they the largest? And this could be, these values could be maximized at different locations along the beam, right? So we need to draw these diagrams. We need to figure them out. And we can either use integration or we can use singularity functions to help us solve for them, right? So now, once we found those critical locations, and let's note for some simple beam geometries and loading conditions, the shear force and bending moment diagrams are actually given in the appendix for a few simple cases, something that could be useful during an exam. So now that we've found our critical locations, we then need to start to calculate the stresses inside of the material due to those critical forces and moments. So at that critical distance X that we found, where things are maximized, we start to calculate the different types of stresses. Due to a normal force, we can build a normal stress. Due to a pure shear force applied to a geometry, so near a wall or interface, in a joint interface between two structures, we can have pure shear stress. When a body is subject to a bending moment about one plane, we'll have normal bending stress develop. If we have two moments that cause our body to bend in two directions, two-plane bending, then we'll have to solve for this, two-plane bending normal stress. If our body is subject to just a general shear force that is not pure shear, so like say shear force at the end of a beam, then we'll have to calculate the transverse shear stress. And if our body is subjected to a torque that causes a twisting motion, then we'll need to calculate our torsional shear stress, right? So that's a lot of work of all of these types of stresses that we need to find. And what's key in finding these stresses is knowing what their sense is. Is it a positive normal stress, something that causes expansion, stretching, or is it a compressive normal stress? Is our transverse, is the shear stresses that we develop creating a clockwise sense of motion or a counterclockwise sense of motion, right? So once we figured out our stress magnitudes and their senses, we then need to superimpose those stresses together in order to create a stress tensor, a representation of the state of stress at that critical location. For 3D geometry, we'll have a 3D stress tensor that has 6 terms in it. The normal stresses, and then the 3 shear stresses, which through equilibrium are equal and opposite. So these values are the same, these values are the same, and these values are the same, right? Now that we have this stress tensor, there's a little bit more work that we can do once we have this stress tensor in our hands. One of the things we could do is calculate the stress tensor at multiple critical locations. So say there's a location where normal force is maximized, but it's not the same location where bending moment is maximized. We may need to evaluate these stress tensors at more than one location, because we have to remember that within a body, every point within that body has a unique state of stress that it's subjected to, right? Now, say we've got one critical location. So we've got a beam and we know everything is maximized at this one location. And on the cross section, we even identify that the stresses are maximum in the corner, the top right corner of this geometry. Then there's just one final step that we may need to make in analyzing this geometry. And that is to apply more circle to our state of stress and solve for the location of the first principal stress, the largest principal stress within our body. And, or we may want to find the location, the angle and the magnitude of the absolute maximum shear stress that exists within the body. And these two parameters, the principal stresses and the absolute maximum shear stresses, are some of the simplest criterion that are used for evaluating failure in structures. We're going to learn about those, what we call ductile failure and brittle failure theories within a couple lectures. So with that said, we've covered the steps to solving combined loading problems.